Hello, everyone, and welcome to this Flexible Circuit Technologies webinar. My name is Katie, and I will be your Global Spec moderator. Now I'm going to introduce everybody for today's presentation. So we have our participants listed on the slide here that we've had up on the screen. So for our presenters today, we have Chris Clark. Chris is a Senior Principal Application Engineer. Chris has 35 years of his career designing and building flexible circuits, rigid flex, and flexible heaters, serving applications for most every industry. He is CID certified and sits on several IPC committees, including IPC-2223, IPC-6013, IPC-4202, IPC-4203, and IPC-4204. Joining us today is Zach Shaner. Zach is a Senior Applications Engineer at Flexible Circuit Technologies. Zach has nearly 2 decades of industry experience, and he brings extensive expertise in design for manufacturability, as well as the manufacturing and assembly of flexible printed circuits, rigid flex solutions, and etched foil heaters. So, gentlemen, I'd love to welcome you to today's event, and I'm going to pass things over to Ray Contrell from Flexible Circuit Technologies. So, Ray, go right ahead.
Katie, thank you, and thanks to this global team joining us today for the next event in our Flex webinar series. Today's topics will again be led by Zach and Chris, who have combined roughly 60 years of flex circuit design expertise. Topics today include why someone would use a flex circuit, bending and forming, and termination options. So I'd like to just take a few minutes and provide an overview of the organization that Chris, Zach, and I belong to, and share just a few thoughts on our amazing facilities and capabilities. So we actually just celebrated our 25th year in business. In addition to the industry-leading flex design team that we have, we offer a deep and wide bench of manufacturing services as well. In addition to flexible circuits of all shapes and sizes, we do rigid flex, flex heaters, flat flex, catheters and longer circuits, printed electronics and silver circuits, and a lot of value-add manufacturing, including, of course, putting components on flex, straight PCBAs, plastic moldings, sub-assemblies through box builds. Our world-class facilities in Asia include a combination of facilities in China and now in Thailand. The investments we've made and continue to make are north of $80 million in new capital equipment across a variety of manufacturing services that we provide. We currently have about 1.5 million square feet of manufacturing in Asia. And as we talk about circuit design and opportunities, we can, of course, bring those to market with you in-house. Having launched, thousands of different products in sub-assemblies over the years in the medical market segment, industrial, consumer, automotive, EV, and battery. We carry the needed accreditations as well, including 13485 for medical, 16949 for the automotive industry, and also for 6.3 for German automotive companies. So as you think of us and look forward to perhaps engaging on design conversations with our design team, our model is built on bringing you prototypes, NPI, and full production in a variety of manufacturing services focused on value-add flex and electronics contract manufacturing with plastic molding in-house as well. So on that note, I will turn it over to Chris and Zach. You're in good hands. They do an amazing job. And again, thanks for joining us.
All right, thanks, Ray. So the first segment we're going to cover today is why somebody would choose to use a flexible circuit. And to do that, we're going to kind of go through the different markets that we serve, as well as the many different applications and why flexible circuits are a good fit within these. So medical is definitely one of our larger markets that we support. If you look at the slides here, the pictures here, surgical tools are a big one. So one of the big things that people choose flexible circuits for within a surgical tool would be the ability to withstand sterilization. So oftentimes these are more than just a single-use product. which means they need to go through sterilization between procedures, and flexible circuits withstand this process very, very well. Not only that, these need to be rugged. So these pieces of equipment are tossed around into bins and cycled through, like I said, the sterilization process. So they're not exactly handled super delicately, and flexible circuits lend themselves very well to this application. Catheters is another great market that we've seen expand over the last couple of years. So, typically these have a proximal and a distal end, and historically they were connected by wires. These wires are very, very small, 20 or 30, plus gauge, 38 gauge to say 44 gauge in diameter. So with being that small, they're delicate, difficult to assemble. So you're going to have to make a connection on one end or the other. And by going to a flexible circuit, you now have one circuit that spans from your proximal to your distal end, and it's easier to install within the catheter. We can support these circuits up to 1.5 meters long pretty easily. In some cases, we've gone up to 2 meters. It just kind of depended on your specific design and what kind of processes that we need to run the part through. Hearing aids. So you think about a hearing aid, and they've certainly gotten smaller over the last 20 or 30 years. So another great fit for a flexible circuit as they're trying to get more functionality into a smaller footprint. Going from wires to flexible circuits has just been kind of a natural progression. Imaging equipment, so MRIs and CAT scans have flexible circuits in them. And then similar, most all of your equipment within an operating room or doctor's office, if it has electrical functionality, oftentimes these have flexible circuits in them. And then, personal use continuous glucose monitors. As diabetes has become more and more common, these allow patients to live with that ailment much easier and not get in the way. One of the other very large markets that we support is automotive. So certainly over the last, say, 5 years or so, the big push has been EVs. And most commonly for flex circuits anyways, that we see is in the battery systems themselves. So these are large battery systems that need to be monitored for both voltage and temperature to monitor the health of the batteries and the strength of the batteries, as well as the temperature, because we know that to accept a charge, they have to be at a certain temperature. So oftentimes our flexible circuits will be mounted with different thermistors and stuff like that, as well as connections. We can weld nickel tabs on to make connection to the batteries, and then we can also attach our circuits within a carrier or a frame that allows easy assembly for the manufacturer themselves. But then, looking beyond the EVs, we also do a lot of stuff in transmissions and instrument clusters, heated seats and mirrors and things like that. And again, the overarching theme is that circuits provide reliable service, lower mass, and great functionality. Consumer electronics are another great big market. I mean, if you look at these devices, most all of your earbuds and headphones and cell phones all have flexible circuits in them, or most of them do anyways. And it's kind of been that natural progression where as these things get smaller, people go from wires to flexible circuits. Unmanned vehicles, this is another technology that's really taken off in the last 5 to 10 years, and it doesn't just have to be in the air. There's applications that use these land, sea, and air. So again, these are typically battery operated systems. So the battery has to be monitored for temperature and battery health, but then you're also making connections to the motors and different control mechanisms. And these are a great fit for flexible circuits. When you think about a drone, lighter is definitely better because you're going to get more battery life as those devices get lighter. Aircraft. So looking back 20, 30 years ago or so, the military had a big push where they started converting wire harnesses to flex. And I've worked on applications where they would have a module or a box that was, say, maybe 8 inches by 10 inches and 6 inches deep. And within that box, they had many many different wire harnesses with connectors on the end. Well, they're seeing issues on a couple different fronts. Operators would accidentally plug the wrong connector into the wrong spot, so right out of the gate, they had to take these enclosures apart because they didn't work right. And then one of the big ones was if a wire would accidentally get pinched while they were, putting the lid, so to speak, on the enclosure, it may not fail right away, but you could have a latent failure, 6 months, a year, 2 years down the road, as the plane sees different temperature cycles and shock and vibration through turbulence and takeoff and landing. So again, they kind of recognize that, hey, if we go from a traditional wire harness to a flexible circuit, now we have a more reliable product. Munitions. So we don't do a lot in this realm, but I think it's important to talk about them because just the ruggedness. So munitions often see, 20,000 Gs, and flexible circuits withstand that. They're lighter, they have less mass, so it's just a great application for a flexible circuit, and it really speaks to the ruggedness of our product. So if we think about flex and rigid flex, we enable technology for a new generation of products, and what I mean by that is we've talked a lot about these different applications, and as time progresses, things get smaller. We're looking to get more functionality and less space. So if you look at the upper image there, traditionally that would have been 8 rigid PCBs connected by wires, or possibly flex with ZIF connectors or Z-axis adhesive. But by putting everything on a single substrate, this is now a rigid flex product, and you're able to get all of your components and your connectors and everything in one package that all folds up nicely. It's light and reliable. When we think about flex, it's important to think about the total cost of ownership. So if you compare, the cost of a wire to the cost of a flex circuit, just on the surface, of course, the flex circuit's going to be a little bit more expensive. But when you factor in the reduction in assembly time, you no longer have an operator taking all of those individual wires and plugging them in. Fewer wiring errors. You don't have to worry about somebody putting a red wire where a white wire belongs. And then better electrical performance. The flexible circuits lend themselves very, very well to great electrical performance because the conductor width is very consistent. The space from conductor to conductor is very consistent. And then as you start adding layers of material, the dielectric between your signal layers and your shield layers is very consistent as well. So generally, it's just a much better electrical performance. And then weight itself, you can figure roughly a 40 to 50% weight savings when you compare a flex circuit to traditional cabling. And oftentimes this is due to the reduction or elimination of insulation and extra shielding that comes with those cable harnesses. And then also oftentimes, I talked about with catheter applications, they're so delicate that oftentimes people are using wire gauges that are much larger than they would actually need to be just for mechanical strength. And you can kind of do away with that when you go to a flexible circuit. The coppers are relatively thin, and you can etch conductor widths that are pretty narrow, so you can get a lot in a relatively small footprint. Reliability. So there's been a lot of talk about reliability, and the Mill Handbook 217 did a comparison a few years back where you could expect to see just under 500,000 hours of longevity with a traditional wire harness assembly. And by converting that to a flex assembly, you're over 2 million hours. So roughly 4 times the longevity or mean time between failure of a flex circuit as compared to a wire harness. And with that, I'm going to turn it over to Zach, and he's going to talk about bending and forming.
All right, thanks, Chris. So bending, forming, flexible circuits, so I'll kind of go over a little bit of the content that I'm going to cover. So the importance of symmetry in flex and material recommendations, the neutral bend access of a flexible circuit, aspect ratios for static and dynamic bending applications, tension, compression, and bending concerns associated with tension and compression, some design guidelines for flexible circuits, thicknesses, vias, and pads, different process indicators, failure modes for formed conditions, cold forming versus hot forming for flexible circuits and pros and cons associated with them, as well as examples of manually forming circuits, and as well as tooling that can be used to form circuits. So in this first example here, you have a single-sided flexible circuit. It's on a adhesive clad laminate with an adhesive polyimide cover layer. So it is perfectly symmetrical construction, or an example of a symmetrical construction. If you were to take this circuit, bend it up on 90 degree, you can see the compression force that the circuit's going to see on the inside radius compared to the tension force that it'll see on the outside of the bend radius. So the neutral bend axis for this kind of a construction is really going to be exactly where we want it to be, on that copper plane. So when we're talking about circuit design and symmetry, we're really trying to design the boards with the conductors on the neutral axis, neutral bend axis, or close to it as possible. So different properties that affect the location of a neutral bend axis. The bend axis will shift towards layers with heavy copper conductors, copper planes. It will shift towards layers with thicker polyimides, thicker cover lays, thicker bond plies in the construction. Heavy copper layers or thick polyimide layers on opposite sides of the neutral bend axis tend to cancel each other out. So again, we're talking, that statement talks a little bit more to symmetry in the construction, as a balanced construction will tend to keep the neutral axis in the center of the stack. So a few different examples of bend radius here. We have 180, 90 degrees, 45 degrees. With 180 degrees, we do have applications where, you know, we're required to actually bend a circuit back onto itself and actually crimp it. There can be concerns, you can compromise conductors, but in some situations that's perfectly acceptable. Another thing to mention here is if a circuit is very thin or using very thin materials, to be able to achieve some of these different radius, you actually have to bend the part further as the material, the nature of the material is it really wants to relax back to its naturally flat state. So any of these radius or any radii in between are definitely possible. It just depends on what kind of tooling and how you're going to actually get to that finished state. So you can see in this slide here, you have a circuit on the upper left with a very tight bend radius compared to a very nice gradual bend radius to the one on the right. If you were using or if you had a dynamically bending application, it's nice to have a nice gradual bend radius like that on the right. If you were to do dynamically bending with a tighter bend radius on the left, you could start to see some concerns with some of the instances that we'll see on some of these upcoming slides here. So bend ratio. So the bend ratio is the bend radius in relation to the circuit thickness. So if you had a circuit that was 4 mils thick or 0.1 millimeter, looking at the guidelines here on this next slide, for a single or a double-sided circuit, IPC 2223 would suggest that your minimum bend radius be 10:1. So if it was a 4 mil thick circuit, you would be looking at a 40 thousandths bend radius or 1 millimeter bend radius. That would increase to 20:1 for a multi-layer circuit. And for dynamically bending applications, the recommendation is 100:1. Just to throw this out there, these are guidelines. A lot of time, you really, it's very application specific, what kind of environment it's in, the materials that you're actually using. You can violate these guidelines, and for your specific application, it might be just fine. But these are the recommendations that, that our industry tends to follow. So getting into some of these concerns with a bend radius, this example here, you can see a double-sided circuit. On the outside of the bend radius, you can actually see where the part under tension has fractured, and as has the polyimide. And you can kind of see on the inside, there's some buckling. So you can also see in this construction that it is asymmetrical. You can see the cover lay on the inside bend radius is significantly thicker than the outside, and the bond ply in the middle between the layers is very thick. So the neutral bend axis is much closer to that thick polyimide than it is that outside conductor, which due to that compression, we are getting separation of that outermost flex or the outermost conductor, as well as that polyimide layer. Here's an example of a 4-layer. Again, you can see we already have a hairline crack under the tension of that outermost layer and some buckling on the inside. So again, in these instances, the bend radius, it definitely is violating that the construction can allow. And in these kind of instances, if you had a tighter bend radius, doing things like electrically testing, post-forming is very important to know that you have not violated the bend ratio of your design. So again, the cover lay wrinkles, this is on the inside of this bend radius, this is a really good process indicator that you're violating the bend ratio that your circuit should be able to achieve. And buckling doesn't necessarily mean a failure, but it does mean that you are compromising that material. And for this application or for this circuit, if this was in a dynamically bending application, that buckling could, after so many bends, delaminate and propagate throughout the circuit. So again, it's not a failure mode, but it is a process indicator when you're seeing these wrinkles or these buckling that bad things could happen down the road. So it's just another thing to watch for.
Hey, Zach, we have a question. Are these cross sections or microscope pictures? Can we see the cracks under a microscope?
Yes, you can. So these are all taken via cross-section. These are all cross-section pictures. And yes, you can definitely, in the pictures, see, maybe not in the pictures that I have here. I mean, you can kind of see it here, but depending on how much magnification we use in a cross-section, you can most definitely see hairline fractures, separation, all of these different things. So some good design guidelines to follow if you know you're forming a circuit or have a dynamically bending application. Keep small conductors to the inside of the neutral bend axis. So if you had a double-sided part with signals on one layer, a shield on the other, it's best to design those signals on the inside of the bend radius. Attempt to keep single plane layer close to the center of the material stack, which we saw in the very first slides that we went through with that single-sided example. Determine and evaluate your bend ratio. Utilize rolled annealed copper. Rolled annealed copper does have significantly higher elongation compared to electrodeposited copper. Indicate copper grain direction on the print or provide forming or bending. We do get quite a few prints that come in that show the part in its formed state. And that is very helpful so that we can actually help to provide direction as to how to orient the grain direction and provide guidance if it looks like the radius you're trying to achieve is going to violate that of what the design is actually capable of. Don't go too thick, don't go too thin. We've had the most success, 1/2 ounce and 1 ounce for dynamically bending or static formed circuits typically seems to work best. We have seen fractures on 1/4, 1/3 ounce, a little bit more, or that of 2 ounce or more. It seems like the sweet spot for dynamically bending or tight bend radius, it does seem like that 1/2 ounce to 1 ounce is kind of the sweet spot. Avoid pattern plating copper. So when you have a double-sided or higher layer count part, doing pads only plating to not deposit any additional thickness, any additional copper. Electroplated copper is not as ductile as just the rolled annealed copper, so eliminating that from your flex can be important. and then utilize unbonded areas to increase flexibility, which we're about to jump into on the next slide. Once I pick it. So here's an example of a multi-layer circuit. You can see it's on a pretty gradual radius actually, but even that, it can be a little too aggressive when multiple layers are laminated together and then bent or formed. So there are things that you can do about that. One thing that you can do is selectively bond the circuits just at the ends that need to be laminated, drilled, plated together, and the rest of the flex straps unbonded. So doing a design like this, which would be basically an unbonded design, can help to provide significantly more flexibility, being the materials are not laminated together. Sometimes that can actually hurt you though. So in this example here, you have 5 independent flex straps, but with how this part is formed, you can actually see that the flex straps on the left-hand side are under significantly more tension and compression compared to the flex strap on the right-hand side. There are some things that you can do about this. There are some design constructions, like for example, a book-bound part where the flex straps are actually at different lengths, so everything will bend and be on the same, basically the same length in the formed state. However, those kind of constructions can come with a higher tooling cost and overall higher cost just because of what's involved in the manufacturing of a book-bound circuit. So some additional design guidelines: keep plated through holes as far away from the bend area as possible. So any vias or plated through holes, try to push those away as far as you can. Ensure that conductors pass through the bend area at 90 degrees to the bend. So that's also important. You want to bend the conductors perpendicular with the bend itself. So if you were to bend a plated through hole, as you can see in this picture here, you have the tension on the outside, compression on the inside. You can see a significant amount of buckling. Keep in mind too that when we are plating vias and even pads only plating like this, it is electroplated copper, and chances are you're going to compromise the integrity of that via if you are bending it. So it is important to, if at all possible, move any vias as far away from the bend as you can. This picture here shows an example of routing the conductors straight through the bend or completely perpendicular compared to the appendage on the right, which is at a 90. The flexed appendage on the left, that would be the proper way of doing it. You really want to try to not bend or form the circuits at a 45-degree angle like that's shown on there. It's just, you can compromise the integrity of those traces if you are not bending them completely perpendicular with the trace routing. So the I-beam effect. So the I-beam on the top of this picture here, that's not a great design practice. However, with some of the designs that we're building and the line width and space, it can be challenging to avoid. However, if at all possible, trying to avoid the I-beaming will help to make your part a lot more flexible and a lot more reliable. So if you can imagine bending the part on the top side at a 90 or 180, there's going to be a lot more stress with those conductors all stacked on top of one another compared to staggered like before, like the picture below. You'll actually get a lot more flexibility out of staggering them and not designing with an I-beam. However, again, with some of the sizes of the circuits we're building, this can be difficult to avoid. Ensuring that there are no discontinuities in the bend area, coverlay openings, plated finishes, conductor width changes. So in this example here, we have a flexible circuit with via stitching along the edge. After a few bend cycles, you can see where we're actually beginning to compromise a via, and the dielectric above it is actually starting to tear. A few additional cycles after that, and you can actually see where we're compromising that polyimide pretty bad. And one thing to keep in mind too is polyimide, it does, after you get a nick or a tear, it does seem to propagate. So it's, if you see a part, if you're doing a bend or a form and you're seeing that you are compromising the coverlay, just know that over time that can propagate just due to the nature of the materials themselves. So we talked a little bit about plating. So in this surface finish here, you can see where the coverlay actually meets the surface finish. So surface finishes like electroless nickel, immersion gold, or ENIG, it's not ductile. So the nickel, the phosphorus content in the nickel makes a very nice solderable finish, but you want to not form anywhere near any transitions like this. You want to try to bring the coverlay as close to the pads as you can, because again, this is not a duct. There are some surface finishes that are more ductile, but anything that you're soldering to, you're really going to want to try to avoid bending anywhere near those locations. So now we'll go through a few different forming methods that can be used to form a flexible circuit. So cold forming is going to be the preferred. So basically forming the parts at room temperature. Tooling is generally inexpensive or non-existent. A lot of forming that takes place is just a manual process using crop marks or nomenclature screen printing on a part. It's the least amount of stress on the circuit materials if formed in a cold state. And the effectiveness based on ratio of copper to dielectric would be the best compared to cold to heat forming. Heat forming tooling can be expensive, so typically you'll have to create a die or a set of tools to actually hold, put the part inside, which we'll see in some coming up slides, heat the part, cool it, take it out. So there's not just the tooling that's involved, but the time that's involved. We're getting ovens involved and so on. So again, a lot of the forming that's done with flexible printed circuits are formed by hand, and we can help to provide, like I said, etch fiducials, screened layers to actually show where the bends should take place. Any kind of a radius of a desk could be used to put a nice gradual radius in a part. And again, this is an inexpensive way of accomplishing this. Some pretty simple tooling. So you can see an arbor press here with a blade that has a radius along the edge. You can orient the part onto the arbor press, have a piece of conformance like a silicone rubber on the bottom side, compress the part into the material, and you have a formed part. So this is a pretty inexpensive yet repeatable way of being able to bend a circuit. You could also modify a pair of vice grips. So you can see in the picture here, we have a hand tool, just a vice grips. We have a die set that's been applied inside the grip. You can orient the part in the grips as you see fit, or using any kind of a designator that we might screen print onto the part. Press the grips down, and you have your desired bend radius using, again, a pretty simple tool, but very repeatable from part to part. There's another picture of that one. Here's some more moderate tooling. So again, we bring a press into it. This one would have a male and female die set. We would orient the part into the first set of the die, pin the die set to the top side, bring the press down, and now you have a more staggered and a little bit more complex of a forming, even though, again, this is pretty simple setup. On this part too, you can see a piece of copper was actually added in that step to help to hold the bend. We can apply copper, we can apply additional layers of polyimide. There's a lot of things that we can add, because again, these materials, especially very thin constructions, they're going to want to continue to correct themselves to their flat state. So there's things that we can do to selectively add materials so that they'll want to hold this condition. A more complex tool here that we have here, you can see the part in its flat state. We have a forming tool here that actually works on different axes by manipulating the forming tool by actuating pins in the tool. You can see the pin actuation. And this part here, you can see on the left, we're actually, again, forming this on multiple axes. We have a step on the far right. So this would be more of a complex tool set, but FCT is very knowledgeable on the different tools, either manual, pneumatic, whatever you would need to be able to accomplish the bend that designing these tools to be able to do that. So heat forming, flex circuits do get very fragile if they're overheated and stressed. Heat guns should not be used. There's no temp control. It can vary, if someone was using a heat gun, that could vary from operator to operator, how far they're holding the heat gun. So you should never use a heat gun when forming a circuit. Parts should be cold formed first, then heated and allowed to cool, constraining the fixture. And the proper temp is the absolute lowest temp that would work. So here's an example of a part that was heated with a heat gun. You can see the buckling and delamination that's happening along the edge of that circuit compared to cold forming and then heating the part up in a fixture and then letting it cool down under while in that tool. So that's all I had on bending and forming. I'll hand it back over to Chris.
All right, Zach, thank you. So the last segment we're going to cover is terminations. So generally speaking, any termination method that you're going to use on a rigid PCB could be used on a flexible circuit as well. So this would include the most common ones are connectors, both through-hole, surface mount, ZIF connectors, and insulation displacement connectors. Components, both through-hole and surface mount. Edge card contacts, which is basically just a thick ZIF traditionally used in PCBs. Wire bondable pads, solderable pads, press fit or soldered sockets and pins, and these can be male or female. Unsupported fingers and pins, these could either be sculpted or added after the fact. And then lastly, anisotropic adhesive or Z-axis adhesive products. So through-hole connectors, they've been around forever. There's a couple different examples here. These could be either installed in the flex region or a rigidized flex region or a rigid flex circuit. Mechanical stiffeners are generally recommended, but they're not required. So if you look at the image on the right there, that's just a through-hole connector that was soldered on. There is no stiffener on it, but you can see examples of stiffeners in the part in the middle there where they have been added. Surface mount connectors, these have definitely become more common when compared to through-hole connectors. Through-hole connectors are often done through either hand soldering or a wave application. Surface mount with the new equipment that's available today is very, very fast. The solder paste is screened on or ink jetted on, and then the machine places the connectors, and then it's run through a reflow. So it's a very, very efficient process. These connectors are relatively inexpensive. Mechanical stiffeners are strongly recommended for a flex circuit. So if you look at the image on the far right there, you can see where there's been an FR4 stiffener laminated on, and then the picture in the middle shows a surface mount connector that's been soldered in place. ZIF connectors, so probably the most common way to terminate and connect from a flex circuit to either another flex circuit or possibly a rigid PCB. These are typically only used on flex PCBs, membrane switches, or flat flexible cables. There is a very strict thickness requirement that is recommended, as well as critical edge to conductor tolerances. So these would all be specified on the connector manufacturer's print, and we're very well versed in it. I would say, 70, 80% of the designs we see have a ZIF connector incorporated in them. So we add polyimide stiffeners as required, and then typically the ends would be laser trim or hard tool punch and die to achieve that tight conductor to edge tolerance. Insulation, displacement, or crimps. So these crimps are relatively cost effective. They come on a large spool, many thousands of them on a spool. They're available in male or female configuration. Essentially, the crimp pierces through the polyimide and then makes electrical contact to the copper conductor within the circuit. And then we can add housings. So essentially, when you're done, you have a connector that could plug into its main. Through-hole components. So I would say this is kind of generally dying technology. They're just saying a lot of through-hole components anymore, and I'm talking your traditional resistors or capacitors. More and more of these have just moved to surface mount. The surface mount are cheap and much easier to assemble. You don't have to worry about forming leads and inserting them into a circuit and then soldering them. The machine just pick and places them with surface mount. When you're using these, mechanical stiffeners are definitely recommended for flexible circuits. And then we get into SMT. So this is definitely a more common technology nowadays. They can be put on either flex or rigid sections of a rigid flex or PCB. We would strongly recommend a stiffener for the use of these components. And the thing there is you just want to make sure you're not flexing where you have a solder joint. And you could also actually crack the components themselves. So again, it's strongly recommended to have a stiffener. These things are getting smaller and smaller. 0402, 0201 are very common. And we can place all the way down to 01, 005 components. Edge card contacts, this is a little bit older technology as well. So think of it as a ZIF connector, but for a rigid section. So we can either laminate a flex circuit onto a thicker piece of FR4 and achieve the desired thickness, or in this case, it would be a rigid PCB or a rigid flat or a rigid section of a rigid flex circuit. Oftentimes, the edge will be beveled to aid in installation. And then wire bondable pads. It seemed like this was really going to take off. It seems like it's kind of stalled out where we see it, but not a ton of it. It's certainly not as common as ZIF. For this technology, the big thing is to remember your final finish. So most commonly, it would be soft gold over nickel. NPEG is gaining popularity, and then we've actually seen some customers use ENIG. One thing to keep in mind when you're using this is with a flex circuit, these materials will compress, so you are going to see some mechanical energy loss when you go to use it. And then another very common one and very simple would just be pads that our customers can then solder to. So we can supply these either pre-tinned with solder on them, the solder of your choosing, or we can provide just pads that are ENIG plated, which is a very solderable surface. Then you would attach wires or a device on your end. We also do a lot of this where we would attach the wires and take that assembly step out of your hands, making a more turnkey solution. And then press fit or soldered sockets or pins. Stiffeners would be recommended for soldered pins, and then they're actually required for press fit because you're not going to want to press fit a pin or a socket into a circuit. You're going to deform your plated through hole and damage it and possibly crack the plating. So when using this technology in a flex application, typically the press fit occurs in the stiffener material and not the flex material. So your plated through hole or your opening in your pad that we're going to solder to would be slightly larger than the diameter of the pin. So the pin gets press fit into the FR4, extends through the circuit itself, and then solder makes the connection from the pin to the flexible circuit. And then unsupported fingers or pins. Typically, this is only in flex. It wouldn't be in rigid applications or rigid flex applications. It could be either sculpted fingers, so the actual conductor material itself extends beyond the edge of the part, or it could be a secondary finger or pin that gets soldered on afterwards. Oftentimes, the solder that's used to attach the pin or ribbon to the circuit would be a higher temp or a higher reflow temp. than what you're going to make your termination to on the other end. So when you go to solder that pin onto your PCB or device, you're not going to reflow that higher temp solder that connects the pin to the circuit itself. Big thing to remember here is these are fragile. I mean, they can be formed. They can be used to make a hot bar connection of two flex circuits or a flex circuit to a rigid PCB, but they're fragile. So when we ship these, we're always taking care to make sure that they're in a tray and they're not rattling around. You're going to want to make sure that operators aren't dumping out the tray when they go to assemble it and damaging the fingers. Another option is to actually have a comb connecting all the fingers, and then those could have pin holes in them that allow you to fixture them, get it in place, do your solder operation, and then snap the comb off. And then another common termination is just the use of Z-axis adhesive. So this could be used on to make a connection from a flex circuit or a membrane switch or a flat flexible cable to a PCB. And it's just a piece of Z-axis adhesive that gets laminated between the flex circuit and the rigid PCB. And it allows electrical connection in the Z, but not in the X or the Y. So everything is connected, but not shorted together. And that's all we have. So now we will open it up to questions.
All right, guys, this is Katie from Global Spec. So thank you both so much for a great presentation. So gentlemen, I'll pass it back over to you to start our Q&A session.
All right, thanks, Katie. First off, are you ITAR certified? No, we are not. Most of our manufacturing is actually done in Asia, so we would not be able to support ITAR applications. My mouse got stuck there for a minute. Let's see, we got a question about traces being routed perpendicular or parallel. So Zach kind of covered that in his presentation. You definitely want to route the conductors perpendicular to the bends themselves. All right, what are standard thickness options for coppers and dielectrics? So coppers can go down to 1/4 ounce all the way up to 2 ounce. Now there are some obscure ones out there that are definitely harder to come by and more expensive. You start getting much thinner than a 1/4 ounce and they are not all that reliable. Zach kind of touched on kind of that 1/2 ounce to 1 ounce being the sweet spot for dynamic bending applications. That being said, we do a lot of stuff. 1/3 ounce is probably the most common copper that we use. And then polyimides, kind of 1/2 mil to 2 or 3 mils are the most common. They can go up to 5 or so mils, but again, you start getting beyond that and they start getting expensive and harder to come by. I'm not seeing it now, but there was a question on ZIF connectors and the offset of the polyimide stiffener in the cover, and what do we recommend for those offsets? And definitely refer back to the connector manufacturer on this. So all of the ZIF connector manufacturers have their recommendations on the actual circuit design. So this will outline the actual thickness of the circuit, the critical conductor to edge requirement that I had outlined, as well as the cover opening size and the polyimide stiffener that needs to be added to achieve the desired thickness. Zach, here's one related to your bending. Does the bending limitation change based on feature size? Are small traces more sensitive?
They most definitely can be. So again, we were talking about, 1/2 ounce and 1 ounce kind of being that sweet spot for tight bend radius or dynamically bending applications. We have seen where if traces are too narrow and they go through a pretty tight radius, that they are more prone to fracturing compared to widening them up a little bit. So if you had a tight bend radius on a 3 mil trace compared to that of a 10 mil trace, I would say that depending on where that trace is in relation to the neutral bend radius, you could potentially crack a 3 mil trace before you would do a 10 mil trace if it was under tension. So that is the answer is yes. It's all very application specific, but yes, the feature sizes there, that does come into play.
How do you design for repeated flexing cycles versus a one-time bend to install? I don't know. On this, I would say bigger is better. So the larger you can make that bend radius, sticking with the 1/2 ounce and 1 ounce coppers that Zach talked about, sticking with the guidelines within IPC 2223, that's definitely the best place to start. We've seen flex circuits in dynamic applications withstand millions or more cycles, provided they're designed properly using all the different criteria that Zach provided, and keeping the bend radii as large as possible. Here's one, Zach. How does copper thickness and layer count impact flexibility and reliability?
So again, that kind of goes back to the slide about the ratio of the thickness of the material to that of the, in relation to that of the radius. So if you have a circuit that is static, it's basically a static application. So the minimum is going to be 10-to-1. So if you had a circuit that was 10 mils thick, that 10-to-1 would mean that the minimum inside bend radius, you wouldn't want to go any less than 100,000. So again, that's from 2223. We have plenty of applications that do violate it, and they seem to be fine for those applications. It's all very application specific, but those are the guidelines that 2223 provides.
All right, here's one. Do you have to use biocompatible carrier materials for medical devices? So we build a lot of product that our customers have gone through the work and determined whether or not they're biocompatible. We really can't speak to that. We can use materials that we know perform very, very well. And typically we're not servicing markets where it's implantable type stuff. So these would be short use products. All right, Katie, I think we're good. I think we've answered the ones that have come in. You want to wrap things up?
Yeah, great. Thank you so much. So yes, we do have any more questions that come in. We'll get back to you all following today's webinar. So feel free to ask a last minute question if you'd like, and we'll get back to you. That window is open until we are finished today. And there's an item right in our resource widget. So feel free to grab that on your way out today. There is a PDF in there that you can download. So gentlemen, thank you both so much for a great presentation today. Chris and Zach, it was a pleasure to have you. And thank you for answering a few of our attendees' questions today. So I'll pass it back over to you for any closing remarks, guys.
No, but I think we're good. I don't see any additional questions. And, feel free to check out our website. We have a lot of great information there. And then this presentation will be available. And feel free to reach out to either Zach or myself with any questions you have. Our engineering team loves speaking with other engineers on applications. Having been in the industry for 35 years, people ask me, what do you like about your job? And for me, for sure, is the applications. The product itself is kind of boring and, I don't know, not all that exciting, but the stuff that it goes into is pretty cool. So we look forward to working with you and answering your questions as they come up.